Hi, welcome back. In this video we're going to begin to look at Ampere's law. Ampere's law allows us to easily calculate the magnetic field due to some current distribution. So let us take a look at this. Now, similar to Gauss's law, Ampere's law states that the circulation of a magnetic field H around a closed loop L equals the current enclosed by L. So let's write that down mathematically. The closed line integral over some path of h dot dl equals the current enclosed by that closed path. And sometimes I'll drop the ENC subscripts there, just write I. But this is Ampere's law, and that's so-called integral form of Ampere's law. Now, by applying Stokes' theorem to the left-hand side, which relates a closed line integral to a surface integral using the curl operation, the left-hand side is equal to the surface integral of the curl of h dotted with ds, where s is the surface that is defined by the closed line. And then, so that's the left-hand side, and then I enclosed, well, we know how to determine that with an integral. We would integrate over the surface of the current density dotted with ds, right? Go back to what we talked about with the current density. Now we've got a surface integral on both sides over the same surface, and they're equal, and they're both dotted with ds, so we can just compare the integrands, and we see that the curl of h must be equal to the current density J. And this is Ampere's law in point form, or differential form. And this is the third of four Maxwell's equations now that we are studying, for the static case anyway. All right, so the claim is that Ampere's law allows us to quickly determine the magnetic field due to some current distributions. So that's what I want to take a look at now, some very important applications for Ampere's law. And the first situation is when we have an infinite line of current. All right, so suppose I take my infinite line of current, I'm going to orient it on the z-axis, and we're going to say that it has a current I going up, why not? And then I'm going to ask, well, what's the magnetic field at some point P? Now, in order to apply Ampere's law, I can pick the path L, and I'm going to pick it strategically, though. I would like to pick the path L so that the magnetic field is constant in magnitude everywhere on the path, and everywhere on the path the direction of the magnetic field is either normal or tangential. So I already know from the Biot-Savart law how the magnetic field is directed from this current carrying wire, and it circulates according to the right-hand rule. If I point my thumb in the direction of I, then my fingers curl with the direction of the magnetic field, so it's circulating around this wire. So I'm going to strategically pick a circle that passes through the point of interest like that, and that's my Amperian path. That's like the analogous thing to a Gaussian surface for Gauss's law. Now, this Amperian path then encloses all of current I, so we can write that I, and this is path L, is equal to the closed line integral over L of h dot dl. H is the unknown here. But I do know something. In order to apply Ampere's law, you need to know something about H. And from the Biot-Savart law, we know that H is in the phi direction. So what I can do is replace H with H sub phi, its component, in the phi direction. dotted with dl. So here is dl, here's my little slice of my Amperian path, and I ask myself, what is changing over that little slice? Well, it's not rho because the radius is constant, and it's not z because the height is constant. It's the angle that's been changed as I proceed through the loop. And so dl in this case is rho d phi in the phi direction, like that. And when we do the dot product, a phi dotted with a phi is 1, and h phi is constant on my Amperian path, so I can bring it out. Rho is constant, and so this integral is very easily done. This is h phi times rho, integrate phi, h phi times rho, integrate phi from 0 to 2 pi, like that. So I have my current I is equal to h phi times rho times 2 pi when I do the integration. And in other words, h phi is equal to I over 2 pi rho. And then in vector form, this is I over 2 pi rho in the phi direction, like this. And so you see that was pretty painless to get the magnetic field. We did this actually, we calculated this with the Biot-Savart law. It took us quite a long time, quite a few computations with kind of a trigonometric integral, which actually I enjoy. But this was much faster. I think you'll agree on that. And of course it matches our result from the Biot-Savart law. Okay, so I'm going to erase this and we're going to go to another example of how we can apply Ampere's law. And let's say that we have a sheet of charge now, an infinite sheet of charge. So I am going to orient my infinite sheet on the xy plane, although you don't have to, but you have to pick something convenient. So that's what I'm going to pick, and I'm going to say that I'm going to orient it such that the current is going in the positive y direction. So let's say here's K, and let's say the current is uniformly distributed. So K is equal to just a constant Ky in the y direction, right? Okay, so we're making a few assumptions here. The plane is infinite. Okay, this goes on forever, and we've oriented the plane such that the current is traveling in the y direction, and it's uniformly distributed current. Now, in order to apply Ampere's law, you have to have some idea of what the magnetic field looks like due to your current distribution. Just like in the previous example, we knew that the magnetic field was circulating around the line of current. So we're going to try to get an idea of what the magnetic field looks like due to this thing. Actually, we know what it does because we solved it already from the Biot-Savart law. But let's take the perspective from the positive y-axis. So suppose you're standing right here and you look this way. All right. So if that's the case, you would see the x-axis to your left like this, and the z-axis up and down. And suppose we have just two symmetrical lines of current, and so we're only going to consider out of the sheet for right now, just for argument's sake, two of these arrows that are symmetric, and they're coming out at you because we're on the y-axis and they're going in the y direction. And so this is the notation that we use, or how we depict that. A circle with a dot means coming out at you. So we're just looking at two symmetrical lines of current, infinite lines of current coming out at you. And let's say we're considering the field point up here, P, on the z-axis, and we want to first consider how is the magnetic field directed due to this first segment 1. All right, well, that first segment 1, if you apply the right-hand rule, All right, so you could do this a couple ways, but you could point your thumb um, in the direction of current, which is coming out at you, and then your fingers circulate around the magnetic field. So the magnetic field is circulating right here, and so at point P, it's directed this way. Okay, so this would be dH1. The direction of that is going to be perpendicular, right? I'm calling it D, like an incremental, because we're only considering an incremental piece of the sheet that is one fine line of the sheet. Now we might ask ourselves, what about that? What about that symmetrical piece to the right? Right? Well, that guy. So we can apply the right-hand rule again, right? And so you point your thumb in the direction of the current, which is coming out at you, and then you circle your fingers, right? And so it's circulating counterclockwise around there. And then when we hit P, we notice that P actually goes like this. At P, we have a magnetic field that is directed like this. So we'll call that DH2. All right, so all of this is to say, and you'll notice that the component in the z direction then cancels, right? And we only have a component in the x direction, right? dH. And you say, well, you've only considered two little pieces. Yes, but for every piece to the left of the z-axis, we have a symmetrical piece to the right of the z-axis. So that cancels out, and so we expect the magnetic field to be pointing towards the positive x-axis. Now, for below the sheet, you could apply the same reasoning, and what you would see is that it would point this way. So there's kind of like a torque due to the sheet. Anyway, we'll talk about torque later on in the course. So just so we know how to find H due to a line, an infinite line of current. We did that in the previous example. Now we suspect that the magnetic field is going to be pointing in the x direction, either positive or negative. So when we integrate then from symmetry, H will only have an x component, and this component is negative below the sheet and positive above the sheet. Okay, so that is all to say the following. I am going to, I guess I have to define my Amperian path now. I'm going to define my Amperian path like this, so that it is parallel up here to the x-axis and also perpendicular to the x-axis. When the path is parallel, we'll have non-zero integral, right? And when it's parallel, we'll have non-zero integral, and when it's perpendicular, we'll have zero integral. So here's my Amperian path, and we'll call this segment 1 here, segment 2 here, segment 3 here, and segment 4 over here. And let's give this thing dimensions. Let's say this is A and this is B. So now H dot dl is equal to the integral over segment 1 plus segment 2 plus segment 3 plus segment 4. Right? And that's all equal to the current that's enclosed by my path. So let's talk about the current that's enclosed by my path. Well, I've got K amps per meter flowing through, and how wide is my path? Well, that's dimension B, right? And so I've got K amps per meter times B meters gives me the total current that is passing through my loop there. So this is all equal to KY times B. Okay, so now let us try to evaluate this integral. Since there is, so if I go over segment 1 is in the direction of the magnetic field. This is why we chose such a path, because segment 1 is parallel to what we concluded was the direction of the magnetic field, right? So when I do the dot product is very simple. The dot product is just hx. We don't know what hx is just yet, but it's whatever the strength of the magnetic field is times the length. That's the integral there, h dot dl. Again, since they're parallel, h and b, h and l are parallel. That's what we get. Now when we go through segment 2, what's nice then about segment 2 is that segment 2 is perpendicular to h. And so when we do a dot product, when h dot dl, when they're perpendicular, you just get 0. You see, this is why we chose the Amperian path that we get. Either the path is tangential to the field or it's perpendicular. So we can leverage both cases. Now when we go through segment 3, we're going again with the field. So there are really two negatives here. But we're going with the field. So this is again makes hx times b. That's segment 3. Segment 3 has a width of b, L is b, and then h is hx. So really, since L is going into the negative x direction, that should be negative b, but hx is also going in the negative direction, so that makes a positive. And then when we go up segment 4, again, segment 4, dl is perpendicular to h, and so the dot product is 0 inside that integral, and so that's it. That's our, we've done the integration now. That's really nice, right? That's why we use Ampere's law. So this makes, of course, 2b hx. The b's drop out as they should, because the result should not be dependent on my Amperian path. And so this makes hx equal to 1/2 ky. Now, remember we said that h was positive above the sheet and negative below, so we could say something like this: h is equal to 1/2 ky ax in the x direction, right, when z is greater than 0, or it's negative 1/2 ky ax when z is less than 0. Okay, and then in general, maybe we don't want this to be dependent on how we oriented the sheet. So in general, what you can say is that h is equal to 1/2 k. So now we're just saying, you know, k is just any old orientation, right, cross a normal vector to the sheet, to the field point. And that is our final result. All right, so that gives you a flavor of how we can apply Ampere's law. And I think I actually have another example that I want to work through. So I will see you in the next video. Thank you.